detail, just so that you know what the ground rules are going to be for this course. And then, well, I'll get started with the material. And before I do that, I want to know a little bit from you, so I'll go around the room and you can tell us a little bit about who you are, what your background is, what your field is, and so that we sort of all can learn how to know each other. So, well, first of all, just so that I know, who's officially registered in the course? I'll say quite a few, and there's a few others who are not. Are you thinking of registering or just auditing? Auditing. How about you? You're registering and auditing. Okay, yeah, that's fine. I'm certainly fine with auditing. I have enough, enough of a group to be able to officially take, offer this course as a class course, and as opposed to a reading course. So, so that's fine. Okay, so well, you know about the scheduling for this course. So first of all, I give you a little bit of contact information for myself. So you may need to get in touch with me at some point to ask me questions or whatever. So I've included my phone number in my email. That should be plenty. You know about the course scheduling. So it's going to be Wednesday morning, Wednesday afternoon on Wednesdays, and this is obviously the first class meeting, and we'll have another one this afternoon. Textbooks, so well, it turns out that there's a perfect textbook for this class that was written especially for this class many years ago when I first started to teach this course. And yeah, well, I kept, I lost track of how many times I've actually taught this course. The beauty of this course for me is that I never get bored with it, so it's always a treat to teach it every time. And as I told you, I wrote a textbook for this class many years ago that's available for purchase if you wish, from Cambridge University Press, and I forget how much it goes for, but it's available for, I think, a reasonable price. So I haven't, asked our local bookstores to carry the book. So if you want to purchase the book, you can do it through your own means, through Amazon.com or something like that. I'll let you in on a secret, though. I feel very bad requiring students to purchase my own book for my own profit. So I have, another way for you to consider. I don't want you to tell me about it, though. It's a secret. I don't want to know. But if you search around my website, you'll see a link to lecture notes on my website. And under lecture notes, you'll see Advanced GR. And if you click on that, you'll get a PDF version of the book. It's not quite the final print, the final version of the book, but it's pretty close. So I don't think you'll get a lot more typos than there are in the published version. But if you don't want to purchase the book, or if you want to try it out before you purchase the book, that's the official line you should use with me. You can download the PDF and don't tell anyone that I told you that. So you have a way out if you don't want to actually buy the book. But it's a great book, so I hope you will choose to buy it at some point. And it's a nice binding. It's very sturdy. Good product. I've included a number of additional references in case you're looking around for additional things to read. There are a bunch of standard textbooks that I'm sure you'll have encountered before in your career. So this is an advanced course in GR, but there are no formal prerequisites for it, which is a bit unusual. And in fact, it's a bit unusual that we have a whole bunch of advanced courses in GR in our graduate program, but we don't have an introductory level, graduate level course in GR. So it's a little bit of a problem, but nevertheless, well, we make it work somehow. So the point is that even though there are no formal prerequisites, I do expect you to have studied GR in some way in your past. So I will assume a lot of prior knowledge. I will proceed from that and move to advanced topics. So I will have, the first section of the course is going to be a refresher on what presumably you know, and then a little bit more. But I do expect you to have encountered, differential geometry, vectors, tensors, and so on, covariant derivatives, all of the sort of elementary notions of differential geometry and GR before. I expect you to know something about the Einstein field equations. I expect you to know something about the Schwarzschild solution, some basic cosmology. So I do expect you to have some prior knowledge at the level of the sort of introductory books on the subject. My, classic example for that is either Schutz's book or Hartel's book. Carroll's book is already a little bit more advanced than this, and of course you have other books that are even more advanced than that. So if you have done that in your past, then you'll be fine for this course. If you're a little bit behind that, well, you may struggle a bit, and maybe you'll be able to make it up. Maybe you won't be. If you have concerns or issues like that, you can you can talk to me. But yeah, I will jump in fairly quickly into some of the more elementary aspects of GR, and then we'll move beyond that very quickly. All right, let me say a few things about the grading system. So it's entirely homework assignments and a term project. And 60% for the homework assignments, and there'll be 3 or 4 in the course of the term, and then the term project is something that I expect you to get started on early and work throughout the term, and I expect something substantial. So I'll say a few more things about that. So it's 60% for the assignments, and 40% for the term project. So homework assignments, I don't think I need to say any more than that. I have a whole bunch of problems in the book. I'll select the problems that I find more interesting, and I'll assign them to you, and I'll give you some time to complete them, and I'll mark them, and so on, and so forth. The term project, what I have in mind is something where you do your own learning on a topic of your own choosing, and then you'll share it with the rest of us. So that'll be done in 2 ways. So first of all, you'll pick a topic. So I give you complete latitude on picking your own topic. I'm not going to provide a list of topics for you to choose from. I think a good part of the exercise is for you to go and search around for good topics for you to sink your teeth into. There's only one rule, really, about the choice of topic. It cannot be your thesis topic. You cannot cheat that way. You have to pick a new topic, something that you don't know much about, that you want to learn, and something that interests you, engages you personally. You will have to submit a topic to me before February 8th, and what I need is basically a couple of paragraphs where you explain what the topic is, what you want to do with it, maybe point out a couple of references that you're aware of. That would be a good guide for you to study the topic, and then I will look at that and I will decide whether it's suitable. Is it enough? Is it is it sufficient for a term paper? And then what I'll ask you to do is to really go deep and learn that topic as well as you can. I'm not expecting you to do original research. You may, it's happened before that people just went off on a particular tangent and did something original, maybe not worth publishing, but something that was not part of the material that they studied, something more, and that's great. But I don't expect that. I mean, it's nice when it happens, but it's not something I expect. But I do expect you to do a very thorough review of whatever topic you picked, and then you're going to do 2 things. You're going to write a written report. That I'll read and mark at the end of the semester. And then what you'll also do is to prepare a presentation, an oral presentation that you'll share with the rest of us. So late in the semester, at some point, we'll organize a symposium. Probably we'll have it on a Saturday so that we can all join in, something like that. But we'll have a symposium where all of you will give a 15-minute or 20-minute presentation on your topic, so that all of us can learn with you what you've done. And I think that's been, that's something that's worked really well in the past, and something that I think is very, very worthwhile, and something where you learn a lot, but everybody else also benefits from your efforts. So I think it's a really good thing to do. So the first task for you is really to start thinking about what you might want to do for a term paper. A good starting point that I can suggest is that there's an online journal called Living Reviews in Relativity that has a whole selection of review articles by very prominent people in the field, and it covers all sorts of areas from experimental gravity to quantum gravity to astrophysics to you name it, it's there. So you can search around, and it's a very good place to start. If you have a very complete review article on a given topic, it's a very good place to start learning that topic, and then from the references in that review, you can dig further and pick, aspects of the topic that interest you particularly. So you might search around in that, or you might have your own sources of material that you want to tap into to pick your review paper, your term paper topic. Here's the info sheet. Any questions about that?
How many
Yep.
pages do you expect the report to be, or is Planet FX?
Well, I have to read it, so so I think typically it turns out to be around 20 pages like that. So something where you give me enough substance that I know that you've learned something. I don't want lots of detailed derivations. I don't need that, but enough to show that you really dug into something. And the presentation, of course, has to reflect this. Again, you have to present it in a way that's accessible to the class, accessible to your peers. Again, you don't have to dwell on details. You can present the big picture, the big picture aspect of the topic. Other questions on that? So the intentions are clear with respect to the term paper. That's really a very important aspect of this course, and it's one that's really entirely self-directed. So, of course, I can act as a resource for whatever you choose to go into, but it's really self-directed work, and you have to make sure that you don't wait too long before you get started, because I do expect something substantial, and the earlier you start, the better, especially for the selection of topic. And then once you've selected the topic and we all agree, then you can start reading, and that's really, the starting point. Okay, course content. So, basically I told you about the book, and we're going to be following the book. And the 5 sections that I'm listing here correspond to the 5 chapters of the book. So chapter 1 is really a refresher on what I consider to be stuff that you should know, plus a few extra topics that you may not have encountered before. So for example, as I told you, I do expect you to have a working knowledge of differential geometry at the level of knowing what a metric is, of knowing what a connection is, knowing what geodesics are, knowing what covariant differentiation is. I expect you to know something about the Riemann tensor, the Einstein field equations, and basic solutions to the Einstein field equations. So I do expect you to know all of this, but there's a few extra topics that I've included here that will be important for the rest of the course that I will spend a bit more time in section 1 of the course. For example, I'll tell you a bit more details about geodesics than maybe you've seen before, and we'll start doing that probably today. I'll tell you something about Lie derivatives that you may or may not have encountered before, but my expectation is that you haven't seen that before, so I will spend some time on that because it's an important concept. Killing vectors, you may or may not have seen that before, so I'll spend a little bit of time on that. And a few extra topics like that that I'll spend a little bit more time on, that I consider, that I don't expect you to have seen before, even though in fact you may have. So chapter 1 is really a refresher, and after that we're really launching into the advanced topics. So chapter 2 is about congruences of geodesics, and what that means is that you have a whole bundle of geodesics, and you're looking at what they do in reference to each other. So it's really the study of a network of geodesics, and that's something that plays a very important role in the description of event horizons, for example, because when you're dealing with event horizons, you're dealing with null surfaces. Null surfaces are always traced by null geodesics, and this network of null geodesics on event horizons is an example of a congruence of null geodesics, and the mathematical tools that are required for the description is something that enters directly into the description of black holes, the study of black holes. And we need to, so if you want to do black holes seriously, you have to learn that, and that's what we're going to be doing in chapter 2. Chapter 3 is all about hypersurfaces, either time-like or space-like or null hypersurfaces. And again, we're going to introduce all sorts of techniques to study hypersurfaces, which are basically embedded surfaces in a higher dimensional, a three-dimensional surface in a four-dimensional manifold, for example, but it works in other dimensions as well. And again, the event horizon is an example of this. When you're talking about the event horizon, you're talking about a boundary in space-time that connects the black hole interior from the exterior. It's a null boundary, and therefore it's a null hypersurface. And in order, again, to do black holes seriously, you need to know how to handle hypersurfaces. And that's the purpose of Chapter 3, to introduce all the proper techniques in order to do that. Another aspect of hypersurfaces is that, well, there's such a thing called the initial value formulation of general relativity, where you say, like what you do in all areas of physics, you want to solve a problem by saying that, well, we have evolution equations, but we have to specify initial data at some initial time. Well, the concept of an initial time in GR is a space-like surface, and what you have to do to solve the Einstein field equations is to place initial data on that space-like surface and let the field equations tell you what the initial data evolves to as a result of the field equations. So that's basically what people do when they do numerical relativity. They start a computer simulation with initial data, they evolve forward in time, and the techniques to describe all of this are going to be covered in Chapter 3. So we'll talk about, induced metrics on hypersurfaces, extrinsic curvatures, and we'll consider all sorts of applications of that. Chapter 4 is about the Lagrangian and Hamiltonian formulations of GR. I'll spend quite a bit of time on that. The Lagrangian formulation, of course, is very important. It's usually the starting point of various approaches to quantum gravity, so you start there. The Hamiltonian formulation also is, as usual, sort of derives from the Lagrangian formulation, and it's also something very important. It's something that requires a lot of details, and that's why we need to spend some time. So there's a lot of detailed things that go into these topics. So we'll take the time to do it in the right way. A nice feature of all of this is that once you formulated the Hamiltonian for GR, well, it turns out that the Hamiltonian, in the case of a field theory, doesn't just give you the energy, it gives you way more than that. And there's a lot of information that's contained in the Hamiltonian that we can go and extract and learn something about energy, but also angular momentum, linear momentum, and all these sorts of things. And it turns out to have a very rich, structure, a rich, baggage that comes with it. And I think it's very worthwhile to look into that. One reason to do that, again, connecting to black holes, is the fact that, well, at some point we're going to study black holes. We're going to talk about the mass of the black hole, the angular momentum of the black hole. And to define these things properly, well, it's very convenient to turn to the Hamiltonian formulation of GR as a way of understanding these things. So, the material of Chapter 4 feeds directly into what we're going to be learning in Chapter 5. And Chapter 5 is all about black holes. So I think you see the arc of the course, right? So I really want to talk about black holes, but I want to do it in a very meaningful, sophisticated way. And in order to do that, I have to introduce all the tools that are required. I'm going to do that. But the final outcome is really to employ all of that, all of those tools, and do black hole physics with that. And that's what we're going to be doing in Chapter 5. So in Chapter 5, I'll start with the sort of, the simple solutions. We're going to start with Schwarzschild. We're going to do Raison and Nordstrom by putting charge on it. We're going to do Kerr, but after that, we're going to be able to study black holes in complete general terms and have a lot of fun with that, because we have all the proper techniques to handle that. In particular, we're going to be able to formulate the laws of black hole mechanics the way that they've been, understood for a long time in the GR literature. So a couple of disclaimers about what I intend to do. It's not that I don't like it, but my spacetimes are going to be four-dimensional. I'm not going to do anything in higher dimensions except maybe on very exceptional occasions. So it's not that I don't enjoy the higher dimensional stuff, and I know it's become very popular and very central to many efforts in theoretical physics. but you know, I have to constrain the course in some way, and one way of doing that is to stick with 4 dimensions. Another restriction that I'm imposing is the fact that my black holes are all asymptotically flat, so I don't have black holes in anti-de Sitter space, for example. That's another very popular avenue for theoretical physics, and we're not going to do that here, but a lot of what you're going to be learning here with modification can be imported to, you know, ADS, CFT type context where you have different asymptotic conditions for the space-time. And from time to time, I may make some comments on that, but basically you can consider this to be a very, I don't want to say, but conservative course on GR where we're going to stick with the old school and not go very, you know, much into the more fashionable areas of theoretical physics today. Yeah, apart from that, I think that's basically it. I think it's going to be enough. I think you're going to be busy enough with just old school GR. But of course, it's not a limitation in the sense that it gives you a basis to really go into the extensions that people think about these days. Any questions about any of this? If you're really dying to learn something that I haven't talked about yet, if there's a topic you'd really like me to cover, please feel welcome to ask me about it. I may say no, and the reason why I may say no is because I've done that in the past. So there's certainly been times where you know, students have suggested that I cover a topic. For example, a few years ago, students asked me to talk about the Newman-Penrose formalism, and I was very happy to do that. And you know, there were other topics that were suggested over the years. I'm usually always very happy to do that. The only reason why I might happy to do it this time is because I'm very busy and I'm teaching another course and I'm chair of my department, and that doesn't leave me a lot of time for course development. But don't let that stop you from asking. And in fact, I may well say yes, because I may be turned on by your topic and decide that I really want to do this after all. So please feel encouraged to engage in your own education and take charge of your own education by asking me to cover things, for example, that were not initially planned for. An extension of this thought is that, well, if there's something that's left a little bit confused in your head after a lecture or during a lecture or the day after a lecture, please get back to me. Please, you know, send me an email saying that, well, I didn't quite understand this point. Can you, you know, help me? That will help me to, you know, to really do a better job. And in fact, it's happened a lot in the past where students were, you know, would get back to me after a lecture and saying that, well, could you please get back to that next time because there was something I didn't quite get, or can you expand on this? Can you do this? Can you do that? And the answer is always yes, yes, I will come back. You know, if there's any confusion in your head, I don't want to leave it there. I really want to address it. And if it helps you, chances are it will help somebody else. Typically, you're not the only one who gets confused. It's just that everybody else is too polite or too afraid to do anything about it. So be the brave one. You know, speak up. Well, you're free to send me an email if you want to stay anonymous. But of course, the best thing to do that, of course, is to interrupt me when I'm lecturing. If there's something really unclear that I'm saying, raise your hand, interrupt me, and ask a question. I like that. Everybody likes that. And usually what happens is that everybody's confused, but only one person is brave enough to do something about it. And then everybody's happy about it. And, you know, and we can move on and eliminate the confusion. The problem is that it tends to be that, you know, no one is brave enough to do anything about it. And then I never find out that there was a major confusion that needed to be clarified. So please, again, you know, make sure that you're engaged in this course and that you take action and participate fully. It really makes the course much more lively and fun for everybody. All right. Any concerns? Any thoughts? Okay, so what I'd like to do next, just to get us acquainted, is to go around the room and maybe ask everybody to just say, you know, state their name and just say a few words about where they are, which school they go to, what their field is, and what their background is, just so that I know what you're doing and so that everybody knows what you're doing. So, would you mind getting started?
All right, my name is Robert Pfeiffer. I'm a postdoc here at PI. I'm sitting in because I've never taken an advanced GR course before, so going to hopefully pick up a few new things.
And what's your field?
Mostly in the past I've done condensed matter physics, but I'm sort of drifting into quantum field theory at the moment.
Okay, yeah, interesting. So, welcome.
Thank you.
My name is Neva. I'm a first year PhD student at the University of Guelph. I was in PSI last year. My advisor is Will Slater, and my field is numerical vector.
Hi, I'm Katie. I'm actually a science student at the moment, and saw this in one of the emails and thought it would be interesting to come along. Field undecided because, well, I'm still a master's student, and yeah, just wanted to sit in.
Yeah, and you did the 2 GR courses in the fall. And
Well, we did one.
oh, did one in the fall, and
Yeah.
Yeah.
So this is just for fun, essentially.
Yeah, so you can tag along and decide, if it's suitable for you. Yeah. So welcome.
Yeah, so hi, I'm Robert. Also PSI student. Feel not yet finally decided. I've done some cosmology stuff, but part of PSI is finding out what exactly it's nice. Yeah, also I'm sort of here for fun and to look at GR from another side.
Yep. So welcome.
I was starting a master's program at UW. Master physics. That's what my background is too, in farming.
Your background is what, sorry?
Also in farming.
Oh, okay, yeah. And you're starting a PhD in astrophysics? Yeah.
Or master's.
Masters, yeah. And have you done some GR before?
No, actually, I haven't done any.
Okay, so maybe we'll have to talk. Yeah. How about you?
Hi, I'm Ida. I'm doing my first year in PhD in Memorial Newfoundland, and basically my work is general relativity and working on black holes, a special kind of them, and this one, and I'm glad to be here.
So you're at Memorial and
Yes, and I came here for a few months as a visitor student.
Okay, so you're working with
I'm
Ivan.
working with Dr. Matt.
Okay, and now you're Ivan student?
Yes.
Yeah, okay, very nice. Welcome.
I'm Eric. I'm working with Robert Mann, first year PhD. For my master's, I was working with quantum corrected black holes and looking at their stability. And now for my PhD, I'm looking at relativistic quantum information, specifically like near black holes is what I'm interested in. So hopefully this will come in handy for that.
Welcome.
Thank you.
I'm Wilson. I'm a first year master's student with Rob Mann at the University of Waterloo. I'm looking at gravitational dualities, really relevant to the class.
Yeah, welcome, thank you.
Hi there, my name's Aiden. I am a first year master's student at the University of Waterloo. I'm a student of Akim Kemp in the Applied Math department. And for my background, well, I guess really what I'm in is the physics of information. But what I'm really interested in right now is the structure of space-time, and particularly maybe using some tools from inverse spectral geometry and spectral geometry to eventually, I don't know, it's like quantum gravity.
Yeah, thank you, welcome.
Well, my name is Joseph. I'm a first year's master's student at the University of Guelph, and Eric is my supervisor. I'll be looking at the static gravitational self force.
No special treatment. Yep, thank you, welcome.
My name is Trevor, and I'm a first year PhD student with Laurent Fidel here at Perimeter, so I'm doing quantum gravity.
Welcome. You?
I'm Todd Stearns, first year PhD student with Rob Myers, doing ABS-CFT.
Welcome.
I'm Mehdi. I'm a first year PhD student here, and I'm working with Dinesh actually on quantum field theory and cosmology.
Okay, thank you. Welcome to the course.
I'm Pablo. I'm a first-year PhD student at Waterloo. I've had some experience working on compact objects and quantified theories of gravity. Now I'm also interested in inflation recently. That's it.
And you're working with?
Yayash.
Okay, yeah. All right, welcome to the course.
I'm a former STI student, first year PhD, working with Mayash. My name is Beth. Yeah, I kind of used to hear that. Yeah. I don't know what else to say.
Okay, that's fine. Welcome. Last but not least.
Yeah, I'm Muthu. I'm actually a lecturer at university because I'm kind of in limbo. Finished my master's, not started my PhD yet. So I did a master's in pure math in differential geometry, studied uniqueness of black holes in higher dimensions. I'm kind of looking forward to this course because all that I know about black holes is more or less self-taught, so I want to learn from the expert.
Well, thank you. Flattery will get you nowhere, but I appreciate it. All right, well, that's good. So we have a diverse group, and well, I think it should be an interesting class. So we'll get started. So, fundamentals. So for those who came in late, I'll just remind you that, there's information about the official textbook for the course, but there's also a secret link that you can find from my website if you go into lecture notes, where you can find a PDF version of the book that you can download for free and not tell me about it. And that's an avenue for you to get the course material without having to spend money. So after today, you can download the PDF or do it right away if you're online. So everything that I'm going to do except for, I should tell you that I'm going to be following the book. I'm not going to sample all the topics that are in the book because there's a little bit too much for a 12-week semester course. So I'll be sampling in the book. What I really like to do in lectures is not necessarily follow exactly what I do in the book. I like to find alternative ways of introducing topics that I think give you a different point of view, so that if you read the book and then go through your lecture notes, you'll see that there's complementary material that help you, I think, understand the topic better. So I really, in the lectures, I really try to go around the book more than follow directly the book. So the derivations will typically be a little bit different. I'll emphasize different things or introduce different techniques. And to me, that keeps it fresh, that keeps it more interesting. And I think for you, it's value added because you have alternative points of view on most everything. So we're dealing with basically, throughout the course, except for very rare exceptions, we're going to be dealing with 4D spacetime. And 4D spacetime really means that we're dealing with a manifold, which is defined in the usual sense of differential geometry, thank you. And we have a manifold and we have a metric on it. And that's that's really what the definition of a spacetime is. And if you read Wall, for example, if you read Carroll, they'll spend a lot of time explaining what a manifold is, and they'll spend a long time saying that you can have a manifold without having a metric, which is very true and very relevant to all sorts of areas of mathematics and physics. But in our case, we're going to be happy to have a differential manifold with a metric on it, and we won't need to deviate from that. Now, if you read the more advanced books like Wald or like Carroll, they do a lot of work in a very abstract formulation of differential geometry. And what I decided to do in my book, and what I'll be doing in my lectures, is to take a very pedestrian approach to that. And again, it's not because I don't like the abstract approach. In fact, I love it. I mean, I really like this stuff. It's a very nice way of, conceptually thinking about what you're doing when you do, mathematics or physics on manifolds. And, I could, for example, I could have, adopted this way of doing things where you first introduce the manifold in a very abstract way, then you introduce charts to start, talking about coordinates, and then you have mappings from manifold to, to coordinate patches and things like that. And then you have various, maps that relate, tensors on manifold to their coordinate descriptions in coordinate systems and various things like that. It's very beautiful stuff. It's just that it takes a while to do all of that. And what I wanted to do in my book and what I wanted to do in the lectures is to do it in, a very direct economical way, because what I'm really mostly interested in down the road, what I really want to teach you in this course is to calculate stuff. The abstract aspects of differential geometry, I think, are very important and essential from a conceptual point of view. I mean, it's really the way to properly understand conceptually what's going on with the mathematical techniques. But when you want to calculate something down the road, well, you always have to introduce coordinates. You always have to get your hands dirty and evaluate the components of a tensor and do various things like that. And when you're at that stage, you have to introduce the coordinate description of vectors and tensors and everything else. And I just decided to skip a step and do it all from coordinates from the start. So this has a flavor of going back to prior to 70s, where it was all done in, pedestrian coordinate language, and that's an unfortunate, aspect of this. But I still, maintain that this is what I wanted to do. So we'll skip with, the really abstract stuff. So I won't be talking about charts. I won't be talking about pullbacks. I won't be talking about, mappings and various things like that. But that's by no means a discouragement on my part for you to study these things. In fact, I consider that to be an essential aspect of learning differential geometry, learning GR. It's part of what people know. All the experts in the field know this stuff, whether or not they use it heavily in their day-to-day research. Okay. So what do we have when we have a manifold and a metric on it? Well, so typically, we have, I had to say it, right? We have a coordinate system. X alpha. Alpha is the usual, Greek index that runs from 0 to 1 to 2 to 3. And time is usually the 0th coordinate, and then the spatial coordinates are from 1 to 3. So here I'm using the Greek indices as opposed to the Latin indices that Wald or Carroll would favor. So here I'm going back to the old notation because that's what I learned when I was a student. So alpha would go from 0, 1, 2, 3. The coordinate system may cover the entire manifold. That would be the rare occasion. Typically, it will cover a small patch. And then you can cover the whole manifold by, having one patch and then another patch and then another patch and cover the entire thing that way. Typically, we don't have to worry too much about coordinate patches. Typically, we work in a region where one coordinate system is good enough to do everything we want to do. We have a coordinate system. We're going to, of course, have more. We're going to have things living in the manifold. So we're going to have vectors. And in the old abstract way, in the modern abstract way, vectors would be defined as essentially differential operators on a manifold. I'm not going to dwell on that description. One thing to remember, though, is that in curved space-time, in curved manifolds, unlike what we're used to in elementary vector calculus, when we first learn about vectors, we think of a vector as an arrow that points from one point to another point. Well, that's a big no-no in curved space-time, because if you have a curved manifold, if you have a vector on the manifold, it's going to stick out of the manifold. So there's really, there's a base point for sure, but there's no target point for the vector. So we cannot think of a vector as something that points from point to point in curved space-time. So that's really not the proper description of a manifold, of a vector. Instead, what we have to think of is a vector that lives in a tangent space attached to a given point on a manifold. And in fact, the best way of thinking about a vector is to think of it as always, being tangent to a curve. So the proper really way of thinking about what a vector is on a curved manifold is to think of it as something tangent to a curve at a specific point on a manifold. So it's tangent to a curve at one point on the manifold. So a picture of that would be that, here's a piece of the manifold, which is supposed to suggest that it's like a curved surface or something like that. We have a vector that's given at one point. I'm going to draw it as a vector, but as an arrow, but of course I'm not supposed to do that. The vector is defined at that point P, and I can think of that vector as being tangent to a curve that would go through P. If I talk about another vector over here at some different point, I would be thinking of that vector as also being tangent to a curve that goes through that point. And sometimes the curve would come first, and we would construct the vector as explicitly being the tangent vector to that curve. That's very often done. That's how we define the velocity vector, for example, of a particle moving in space-time. But sometimes the curve would come second, so we would be given the vector, and we would think of the curve as being the integral curve associated with that vector. So, which comes first depends on context. A very important aspect of this is that vectors at different points are not related in any way to each other. You cannot add vectors at different points on a manifold. This vector over here really lives in a very different tangent space as the vector over here. And you cannot vectorially do things unless you refer to the same base point, the same tangent space at that point. So there's no such thing, for example, as integrating a vector field on a manifold. Integrating a vector field would mean that you take vectors at many different points and you add them up. That operation doesn't exist. So in space-time, you can integrate a scalar, and that's all you can do. Okay? You cannot integrate vectors, and by extension, you cannot integrate tensors. You cannot add vectors that would be defined at different points. So all vectorial operations have to refer to either this point or that point. If you have two vectors defined at that point, you can add them up, no problem. But if you have two vectors defined at other points, at different points, then you cannot do anything with them. Of course, we'll talk about covariant differentiation, which is all about finding ways of combining vectors at different points and comparing them. But that's not, that's an operation that requires an extra structure, and that's what we'll have to think about. Okay, so so that's our notion of a vector on a manifold. We have something called, a variation on what a vector is. It's called, I like to call it the dual vector. Sometimes it's called the one form. And this is something with an index down. And those things are defined, so in the abstract way, they're defined as operations on vectors that give numbers. Right, so more formally, it's a linear mappers and real numbers, or you can make that complex if you're interested, but we don't have to do that here in GR. So it's really a linear operation on vectors that yields a number. The reason for, I think you've encountered that before. So the linear operation is simply that You take your dual vector, you act on it with an ordinary vector, and you get a number, and the number is, well, the inner product between the two things. If you don't have a metric, there's no direct relationship between a vector and a dual vector, but of course the metric, as we're going to see in a moment, introduces a relationship because you can lower and raise indices with the metric. I like to call it a dual vector. That's just my own preference. Probably more often it's called the one form. The reason why I don't like to use the term one form is because it sort of begs the question, if you're going to talk about one forms, you should also be talking about two forms and three forms. And one thing that I also don't do in this course is to talk about forms. I don't do external derivatives in this course, again, not because I don't like it. I have to confess that I don't like that stuff as much as I probably should. I never really learned it all that properly. I mean, I have learned it, I have used it in the past, but it's never something that I've used a lot in my career, so I've always tended to do without it. You're going to see a lot of form-like things happening in this course, but I'm not going to spend a lot of time telling you about forms in this course. In fact, I probably won't say very much. So while a one form has one index, a two form would have two indices. It would be a tensor with two indices, with the extra requirement that it has to be an antisymmetric tensor, and a three form would be a fully antisymmetric three-index tensor, and so on and so forth. So anyway, to just avoid opening this can of worms, I just won't use this terminology here. Okay, so we have these things, and then we have generalizations of that. We have tensors, which could have any number of indices with any placement whatsoever. So we could have a tensor with two indices up, for example. We could have a tensor with one index up, one index down. And we could have another tensor with two indices down. And of course, I could make a complete listing like this with three indices, four indices. We'll go to four indices, of course, when we talk about the Riemann tensor, but it's pretty rare that we have to go beyond that, although it's by no means unheard of. And you know, these things in the abstract language would be defined again as operations either on vectors and one forms that produce numbers. And again, you know, in order to produce numbers, what you would do with this guy, for example, is to act on two of these guys. For example, by constructing something which again is a number and would correspond to, well, the number that you get when you operate with t on two different dual vectors. And then for this guy, you would operate on a p and an a to get the number, and this guy would operate on two vectors to get the number. So tensors in abstract differential geometry are defined as linear maps between vectors or one forms into real numbers, and then you can generalize this even further. So in my more pedestrian context, I'm happy just to use the the component notation like this. And in the book, I'll talk about how these things change if you make a coordinate transformation. So the point there is that, well, to make a tensor, it's not enough to produce just a whole bunch of numbers and give them, you know, a name and some indices. They have to transform appropriately if you do a coordinate transformation. And I think you've seen this stuff before, so I don't think I need to dwell on that. But it's very important to, it's often very important to recognize whether an object is a tensor or not. And one way of testing this is to test whether their components transform appropriately under coordinate transformations. Although usually we try to come up with more clever ways of testing that. And we'll probably talk about that a little bit later on, even today. So really, those are the most, I would say, the most basic objects that we place on a manifold. There's one particular tensor, of course, that's preferred or more important than others in GR. We're going to place a metric tensor on the manifold. And that makes it, of course, a metric space, and that gives us a notion of distances in space-time. So the metric tensor is defined in such a way that, of course, we have a notion of distance between neighboring points. So in a lot of spaces, it's very important to define a distance between points, and that's something that's very familiar from physics and very familiar in special and now general relativity. And the metric has a dual role, and it's a bit of a funny thing. So its first role, in fact, its first definition is to convert a coordinate increment into a physical distance. So the coordinate increment between 2 points, of course, depends completely on the coordinate system. So that by itself doesn't mean anything in terms of distance information. You always need a rule to convert a coordinate increment into a physical distance, and that's the role of the metric. So the first role is to convert coordinate differentials into physical distances. And in most situations, a metric would just be required to do that. It's just a conversion from coordinate to physical distances. But of course, in GR, we wanted to do more than that. It also is supposed to contain gravitational information. And that's really, for us, the most important or the most interesting thing. It's supposed to describe gravity. The problem with the metric is that it's very difficult to disentangle these things. So when we're presented with a metric, we get both. Whether we like it or not, we get the coordinate information, and possibly we get also the gravity information. But the gravity information typically is buried deep somewhere inside the metric, and sometimes it's very hard to bring it out in a meaningful way. So for example, I mean, if you're presented with a metric that looks very weird and very strange, it may still be the metric of flat space-time, just presented in a very weird and strange coordinate system. And unless you do some tests on the metric to figure these things out, you may not be able to recognize that, and you may think that this is representing a weird and strange gravitational field. So to actually extract the field information from all the extra stuff that really has only to do with coordinates is something that requires more knowledge, more techniques. And of course, you know that I'll be talking about the Riemann tensor, which is really a good diagnostic of whether or not you have gravity, much more than the metric is. But the metric is always the starting point. You start with the metric, and then you derive everything from it. The metric is something that we also use as a tool to convert from vectors and one-forms and different types of tensors by lowering and raising indices. So that's something that we could not do if we're not dealing with a metric space. We would have to keep these objects completely different from each other. But once we have a metric and once we have the ability of raising and lowering indices, then the distinction between a vector and a dual vector becomes a little bit lost, becomes less important. And in fact, I'll probably stop using the distinction very soon. I'll talk about vectors, whether or not I'm talking about an index up or an index down. So in order to, so we have the metric tensor. I'll just introduce the inverse metric. And by inverse metric, I really mean the matrix inverse of the original matrix representation of the metric. So metric and matrix are close words, so it's a little bit funny to say that sometimes. But basically, the idea here is that I'm considering this to be a 4x4 matrix, and this would be, with the indices all up like this would be just the matrix inverse of that 4x4 matrix. And a way to define that properly is to say that, well, if you take the inverse metric and you multiply that by the metric itself, you get the identity matrix. and the identity matrix has a bunch of zeros or ones in it, and that's represented by the Kronecker delta that I have there. Once you have that, then once you have the metric and once you have the inverse metric, then you can convert. You can raise indices. You can convert a dual vector into a vector by just applying the inverse metric to it. So that's called raising the indices. And also lower indices, you can convert a vector into a dual vector by acting with the metric. And those are all sort of simple elementary operations that you've seen before, so I'm probably spending way much time, more time on this than I should. All right, any questions about any of this so far? Okay, so far we have a metric space. We're going to give ourselves an additional structure on our manifold, and that's the connection. And the connection will turn our metric space into what's called an affine space. And in fact, well, okay, let me just say that we introduce a connection. A connection is something that has 3 indices, and it's something that, very importantly, is not a tensor. Because it would not transform in the expected way if you were to do a coordinate transformation. That's something that I describe in some detail in the book. Now, again, thinking in general terms, in more abstract terms, when you do differential geometry, you can have a manifold without a metric, and you can have a manifold without a connection. You can choose to put a metric on your manifold, and you can choose not to put a connection on your manifold, and that's fine. You can do the opposite. You can choose not to put a metric on your manifold and choose to put a connection on your manifold, and that's also fine. So you have a metric space in this case. If you place a connection without putting a metric, then you would have what's called an affine manifold. And then you can have both. You can have a metric and a connection, and that's the kind of manifolds we're going to be dealing with. You can have a connection that's completely unrelated to the metric. In principle, when you do abstract differential geometry, the metric and the connection don't have to speak to each other. They can be 2 completely different structures. In GR, we're not really interested in having so much generality, although when people consider alternative theories, that's a freedom that they'll try to exploit. But I'm not going to be interested in that because we're going to be doing GR. What we're going to be taking here is, what we're going to be introducing here is a connection that's going to be very tightly related to metric. We're going to make the connection metric compatible. I'll explain a little bit more fully what it means, but it's going to be symmetric in lower indices. That's also something that's not necessarily required. And it's going to be metric compatible. And for the time being, I'll just say that this implies that the connection is going to be related to the first derivatives of the metric tensor. And that's going to be our essentially our definition for the connection. And in that context, this thing is usually known as the Christoffel symbols. The only point I'm trying to make here is that this is something that we choose to be our connection in GR, we could have, tried something else. We could have chosen a connection that's different from that. For example, in theories involving torsion, there would be an extra component to the connection that would be antisymmetric in the lower indices, and that would also act as an extra field in space-time that also could have, could have consequences in terms of the description of gravity. But in GR, we don't have that. We have a connection that's completely tied to the metric. The role of the connection is to be able to differentiate tensors at different points. And that's very important because if we didn't have a connection, we wouldn't be able to do that. Notice that I told you that we cannot combine vectors that live at different points. So if I'm thinking of introducing an operation of differentiation, I'm sort of stuck because what's the name of the game in differentiation? You take a quantity here, you take a quantity here, and you subtract them, and you divide by the distance. Well, we have a notion of distance, but we're not allowed to take vectors at different points and compare them or subtract one from the other. That's not a valid operation in differential geometry. The way out is to introduce an additional structure, the connection, that will allow us to make that comparison possible. And the way it works is that the connection gives us a way of taking this vector here, transporting it over here, so that we can do the comparison and the subtraction entirely at one point. So the role of the connection is really to give us a transport rule that will take a vector here to here, so that we can compare the transported vector here to the original vector here, and do the difference, and then divide by the distance between the 2 points. That's how we define covariant differentiation in space-time. So in the book, I sort of fleshed this out a little bit more, but I'll expect that here you know all about covariant differentiation. So I'll just come out with the punchline on that one. So so the next step in the sort of the logical development is to talk about covariant differentiation. Which requires a connection. And here I'm going to first talk about how to differentiate vectors, and then that's easily extendable to other forms, other types of tensors. But I want to differentiate two cases. I want to distinguish two cases. I don't want to differentiate too many things, so I'll distinguish the cases and differentiate the vectors. There are cases where you have a vector field that's defined only on a curve. And there are cases where you have vector fields that are defined in an open region in space-time. And I want to distinguish these two cases because it turns out that there's small but fairly important aspects to that. So suppose that we have a vector field on a curve. And I don't know why, but I always like to call my curves gamma. So here's gamma. So gamma is a curve in space-time. And by a vector field, I mean that for each point on the curve, I know what the vector is going to be. So this is point number 1, this is point number 2, point number 3. So I know what the vector is at point number 1, I know what the vector is at point number 3, and so on and so forth. So vector field means that for any point on the curve, I know what the vector is. So the vector is defined everywhere on the curve. But it's defined only on the curve. In this example, it's defined only on the curve. So if I'm asking you what is the vector over here, there's no answer to that. The vector is not defined there. Okay? So that's the first case. The second case, we're going to open this up and we're going to make the vector defined everywhere so that we don't have to worry about the distinction as, between being on the curve and not being on the curve. If my vector field is defined only on the curve, I can only differentiate it along the curve. Because, I can compare values of the vector field on the curve. I cannot compare values of the vector field away from the curve because they don't exist. So here we want to differentiate a vector field A along the curve. So to do that, we need to parameterize the curve. We need to describe the curve in some way. So we're going to use a parametric description of the curve. Which is basically just giving the coordinate description of the curve in terms of some running parameter. So this is, for example, lambda equals 1, lambda equals 2, lambda equals 3, lambda equals 4. So for each value of lambda, I tell you what the coordinates of the curve are going to be for that value of lambda, and that's how you build up the curve. That's what this means. And in this course, we'll play a lot with, parameterized curves. If you're talking about the word line of an observer, typically what you would do is to give the position of the observer as a function of proper time, and lambda would play the role of proper time. In this case, it's just an arbitrary parameter. What I would want to construct here is a notion of dA d lambda. So I really want the derivative of the vector field with respect to the parameter lambda. And if we didn't have to worry about combining vectors at different points, well, all we would say is that, well, the derivative of A at this point would be the value of A a little bit away from 1 minus the value of A at 1. We divide by the d lambda, and that's our derivative. And that would be the notion of derivatives that we would, start with in ordinary differential calculus. But here we know we can't do that because we cannot straightforwardly compare the value of the vector away from 1 with the vector already at 1. So that's not a valid operation, as I said. That's where the connection comes in. And the notion of covariant derivative is as follows. So I won't derive all of this because I know that you've seen this before. But what I say is that the covariant derivative of A along the curve, I'll use the notation capital D as I do in the book, d lambda, is just mathematically what you would do straightforwardly if you were given the, so you're also given, so we're given the parametric description of the curve, but the vector field, of course, is also known as a function of lambda. So these are functions we can differentiate. So that's what we're doing here. But to that, we're adding the ingredient that allows us to combine vectors at different points by doing what I said before, which is to in fact carry the vector at d lambda, carry it to lambda equals 1, and then comparing it with the vector already there, right? So the connection is the rule that tells us how to combine vectors at different points, and the covariant derivative of A at that point is then the straightforward derivative of the functions divided by lambda, but then we had to add this stuff in order to make everything properly tensorial and to make sure that this, for example, transforms as a vector, because none, this or that separately don't, but the combination of both does. Okay, no big mystery here, I hope. So that's something you've done before. The only important distinction that I want to make here, or the only point I wanted to bring forward, is that this is a notion of covariant derivative along a curve. And when you differentiate along the curve, you don't need to know anything about the vector field away from the curve because you're always differentiating in that direction. Usually we write this slightly differently, and I'll come to that in a moment. One thing I can do is to introduce the notion of the tangent vector to the curve and rewrite this in a slightly different way. The tangent vector to gamma, usually I would call it u, but maybe I'll just call it t. T alpha, by definition, is the derivative of the coordinate description of the curve with respect to the parameter. That's what we mean by the tangent vector. And that, by the way, is an example where we introduce the curve first and relate it to its tangent vector as a second step, right? So we're given the parametric description of the curve, we calculate the derivatives, and we apply a vector as a result, and the vector obviously is tangent to the curve. And if I use this notation, of course, I can rewrite the first expression in this form. And that's usually probably how it would be written. Okay. I'll come back in a second to that, so leave yourself some space, because I want to now consider the broader situation where instead of focusing on a curve, we might be given a vector field that's defined everywhere in an open region, and we may wish to calculate the covariant derivative of that vector, not just in one particular, but in all possible directions. So that would be the covariant derivative. So if we're given a vector field as a function of the coordinates now everywhere in an open region, then we're dealing a little bit with a different situation, because before we know the vector field only on one curve. Here, well, we don't care about the curve, and we know it everywhere in that open region. So here's the open region, and the point is that we know the vector field here, we know the vector field here, we know it here, we know it there, we know it everywhere. And instead of being able to take a derivative only in one direction, now we can take a derivative in all directions, because we know that we know the field in all we know how the field will change in all possible directions. So that's a more open version of covariant derivatives. So now instead of taking a derivative entirely along a curve, we can take a derivative along any coordinate direction that we wish. Yep. Oh, yeah. I didn't mean very much by that. So I just mean some region, and by open I mean that, well, it doesn't really have a strict boundary, so I can always go a little bit beyond it. So it's the notion that, if you have a point in an open set, there's always a neighborhood around that point. It's not a big deal. So I just want it defined in some region, without a sharp boundary. So in that case, the covariant derivative can be defined with respect to any direction, and the notation we use for that is that the covariant derivative with respect to any coordinate direction x beta is going to be denoted with a semicolon. So, well, two ways of doing it really. So in the book, I mostly favor this. Sometimes I favor the nabla notation, which I think has become a little bit more fashionable since Wald's book. So same thing. So here the point is that we're differentiating the vector A with respect to any coordinate direction. And that, of course, is going to be given by the partial derivatives of the vector plus the usual connection term that makes the operation legal from a vectorial point of view. So in that case, we're defining something that is now a tensor, because it has two indices. Before we were still dealing with vectors, now we're dealing with a tensor, And the tensor, of course, has to include the straightforward partial derivative term plus the connection term to make everything properly tensorial. Here, clearly, we have more derivatives than we had before. Here, we had, over there, we had derivatives only in one direction. Here, we have derivatives in all conceivable directions. So we have a lot more information in this than we had in that. All right. So you've seen this before. Now I want to go back to what I was saying before. I'll lower it a little bit. The point I wanted to make before is that usually this is written in a more compact way. So if you compare this expression here with what we had before, what you recognize is that, for example, the derivative of the vector field A with respect to lambda is just the partial derivative of that vector with respect to the coordinates times the derivative of the coordinates with respect to lambda, right? And then the next term, as we had it before, are just, again, expressed in terms of partial derivatives. But when I write it in this form, sorry, I made a mistake over here. And when you write it in this way, what you find is that this is exactly what I wrote down before for the covariant derivative with respect to arbitrary directions. Okay, I slightly screwed this up. I apologize, but it doesn't matter because here I have something symmetric under an exchange of beta and alpha and gamma. So I really meant this to be A gamma and this to be T beta so that I can use it. No, sorry. No, yeah, that's right. So I really meant this to be A gamma and this to be dx beta d alpha, d lambda, but it doesn't matter because this is symmetric. And I can exchange those two indices and relabel them without changing anything, and I get the same thing. So it's really the same thing. So what's the point I'm trying to get at? Formally, I can write the covariant derivative of a vector field along the curve in terms of its fuller covariant derivatives, multiplying the tangent to the curve. But I just wanted to make one point clear about this. So there's nothing wrong with this, except if you try to dissociate this from that. The point is that when I'm differentiating A alpha with respect to lambda, I know that I only need information about the vector field along only one curve, right? When I write this, as I made it, I hope, clear before, when I write this, I'm allowing myself to differentiate the vector field along any conceivable direction. And this is information that I may have, but may not have. If I know the vector field only along one curve, I know how to differentiate it along the curve. I don't know how to differentiate it across the curve. When I write something like this, and I write it all by itself, as I did here, I'm telling you that I know how to carry out those operations, and therefore I know what the vector field is supposed to do across the curve. So if you think of this, so when you look at the combination, though, it's not okay, it's okay, because when you look at the combination, you say, okay, you pretend you can differentiate this across all directions, but you only are interested in the directions along the curve, so it's all fine. Just a second, I want to complete the thought. So the package is fine because you're taking the directional derivative of the vector field along the tangent vector, and that's all well defined. But if you dissociate this from that, this by itself is not necessarily well defined if you only know the vector field along the curve. It's probably a small point that I shouldn't dwell on and make you confused about. But I think sometimes it's important to understand the distinction between a vector field that's known only on a curve versus a vector field that's known globally in a neighborhood, for example, of a curve. When you know the vector field everywhere, you can differentiate it along any direction. When you know it only on a curve, you can only differentiate it on the curve. This notation is always robust. It tells you that you only need to know what you need to know. This notation is okay, but it gives a suggestion that you have access to all this information, when in fact you may not. But when you're restricted by this, you're fine. That's all I wanted to say. So yeah, you had a question?
I just wanted to point out top tensor also using another AD.
Where do I do that? Oh, yes, I did, yes. So there's an A over here. Thank you. Did you have I think I saw it. Did you have a question? No? Okay. Oh, okay. Yeah, thank you. So did I create too much confusion for what it's worth? I hope not. You have a question?
Is there a canonical way to extend the vector field on curve to the open region?
No. No. So there's no way. And sometimes you don't care. So you say, okay, I have a vector field on the curve. Sometimes you say, okay, momentarily I need to define, operations away from the curve. So you just make up your own extension. You just decide arbitrarily that the vector will behave this way or that way. And then in the end, you have to make sure that none of this matters, that all of this extra stuff that you're putting in is irrelevant for the end point of your calculation. But sometimes you really have to be careful about this, because it could be that the end point of the calculation will care in a subtle way about what extension you chose. And if that happens, well, maybe there's meaning to that. Maybe there's, there's something, maybe it's something that, tells you what the extension should be. But the point is that you would have to provide all this information and explain why you chose this particular extension. And that can happen in some contexts where you have to, make up an extension and then justify after the fact why this was the appropriate extension for the purposes you had in mind. But the point is that other than that, the choice is always arbitrary unless you have other reasons to incorporate the choice. So there's no way of having a unique extension of a vector away from the curve if you only have the vector defined on the curve. Any other questions? Okay, so I think I'm going to quit here and we're going to resume in the afternoon. So what I won't do, and I'll skip over, is, well, here I focused on a vector, but of course I could generalize all of this to covariant derivatives of, dual vectors, tensors, and things like that. I presume that you know how it's all done. All of those distinctions that I've made between things defined on the curve versus things defined globally apply to all of those things. When you carry out, covariant derivatives for other objects, well, there are rules you have to follow. So typically there's, not typically, always, there's one Christoffel term per tensorial index. And then if the index is up, you have a plus sign. If the index is down, you have a lower sign. You have to learn the gymnastics of placing the indices properly. You have to avoid doing what I did, which is to make a mistake in your equations. That requires, of course, training and experience, but there's nothing very difficult about this. I think the important notions I've covered, the most important notion of all is the fact that differentiation is not straightforward, because you cannot compare vectors directly at different points. You have to invent a rule to take the vector from one point to the other point before you can compare things. That's really conceptually the most important point. What I'll do this afternoon is to talk about geodesics, and I'll probably have time to talk about Lie derivatives, which is another way of differentiating, which in fact does not involve a connection. It's a way of differentiating without a connection that requires a little bit of extra structure, but very little. And in fact, it's an important concept in GR, so I'll tell you something about it. All right, so we'll reconvene at 3:30. Is it? Yeah, 3:30. And I'll see you then.